Okay, great. So let me start off by actually, I thought I'd start off by talking about myself, but I think that's been covered already by Harshit and was also very generous about it. So I'm going to quickly skim through it. So I'm currently EIR at Entrepreneur First, which is a global VC firm, which specifically focuses on investing in scientists and engineers to start impactful companies, mostly what is today known as deep tech companies. So I previously worked in the medical devices industry, computational biology and biosensors. And I started my career a long time ago with a PhD in computational biology. Okay, so thanks very much, and let's get started. So I'm going to start off with a very light-hearted disclaimer because of the topic at hand, right? So we're going to talk about artificial intelligence and biology, but it's very important to sort of clarify that the phrase artificial intelligence and deep learning have been sort of used interchangeably in this topic. I know semantically there are a lot of debates on what exactly this should encompass, but please bear with me during this talk where I use artificial intelligence and deep learning kind of interchangeably. Okay. So what's been happening so far? So if you look at the past few decades, arguably more progress has been made in computer sciences, in the software world in the last couple of decades, especially, and especially out there in the media and also in the industry, you hear a lot being done by the software industry, especially in computer sciences. But that is not the whole story, right? The other world, which is the world of atoms, as opposed to the world of bits, has been at it for a while. The 60s and 70s saw explosive new research being commercialized, new research coming into being. A lot happened. It seemed like the 60s, 70s, all the way leading up to the 80s, the physical sciences were doing a lot more than they are doing today. But this is just superficial. I think a lot of the noise that we hear today is around computer sciences and less so around, let's say, biology. But that's obviously not true. That's not a fair comment to make, because a lot has been happening in biology too at the same time. People have been quiet in biology, but lots have been happening. You see, I think through the 80s, you saw technologies like recombinant DNA technology emerging, which is an absolute game changer. And it is currently considered, commodity technology. And recently CRISPR, for example. Right? A lot has been happening. And biology is very fast changing. Anyone who's been in the lab, I guess a lot of you who've been in the lab, who are currently in the lab and been in the lab in the past decade, can attest to this, that it is no longer the empirical science it used to be many decades ago. It is now almost a directed engineering discipline, right? You have very specific systemic parts that you put together to get a specific output, right? You can now design entire biological systems, right? This is simply because we are now super adept at using nature's own tools to get whatever output that we want. It is almost an engineering discipline. Now, this is partly possible because of the emergence of high throughput technologies, right? So when I say high throughput technologies, I'm sure a lot of you already know what I mean. I mean, technologies like RNA-seq, high throughput sequencing, LCMS, with all these different kinds of technologies which are producing large quantities of data, which were previously unprecedented. We are talking about sampling thousands of genes at the same time, thousands of proteins at the same time, and ending up with large matrices of data, which is very, very different from how biology used to be done. Now, all these different complex types of data are are now amenable to computation because computer science also has been, doing its thing. It's coming up with new methods of, using high dimensional data sets in terms of advanced statistics and machine learning. When we saw all these different, in the past decade, especially, when you saw all these various different kinds of data sets emerge, especially this was true when I was still in the lab, there was a lot of excitement around what would happen in biology when all these different data sets are used for, extracting insights. Everyone was excited. That was the time when the whole space of computational biology sort of emerged from bio plus computer science. And well, when we saw that, we were all excited. We knew all the major issues back then, major hurdles back then, were around predicting functions of unknown genes. You have thousands of genes from gene sequencing projects, and how would you go around annotating them? Previously, the only techniques we knew how to for annotation was actually doing experiments in the lab. Now there was an opportunity where you could simply go ahead and predict the labels of unknown genes. Fantastic. You could also theoretically work out the causality in various molecular pathways. Amazing. I mean, this is what people spend decades on working on one, let's say, signaling pathway, for example. So similarly, the same applies to phenotypes as well. We thought we could simply predict phenotypes based on these high throughput experiments. Now, all we need to do was figure out a smart way of putting all this data together and building some kind of machine learning classifier for the job, and boom, you would have the machine learning classifier would simply do its job and come up with labels for unknown genes, causality in molecular pathways, and how phenotypes appear, etc., etc. Oh, but that didn't happen, right? We kind of slowed down. If you look at the number of papers published in the space, they haven't slowed down. But objectively, if you sort of assess, have we gotten far from where we were a decade ago? Kind of slowed down. Now, why did we? I'm sure many in the audience already know the answer to this, but I'm going to summarize this in a slightly high-level way, and I'm going to call it. So, according to me, one of the biggest roadblocks that we hit was all these high-throughput data sets that we have turned out to be actually super noisy. You know what? Biology itself is super noisy, right? We did not expect to, crash into so much noise and halt our progress, right? The other thing was we had completely underestimated the complexity of biology, right? So if you look at, actually, the image on the screen is supposed to be, I think it's a gene interaction graph or a protein-protein interaction map of I don't remember what. But however, what's important is the complexity of the interactions, right? So that complexity could not be extracted out of the data. Right? We couldn't figure out how to get to an insight from this. And to do that, we had two pretty strong, formidable tool sets back then. One was, good old statistics, which did pretty well until then, and of course the early form of machine learning with clustering methods, multi-label and single-label classification methods, so on and so forth. This is all great, but we at the time didn't know that we were making progress. At the time, we didn't know that we were slowing down. We thought we were going faster than ever, because that's what it seemed like. And we didn't stop. So regardless of what the limitations were of these tools, it was very clear that the age of systems biology had arrived, right? Systems biology is a word coined because we were now able to look at biology as a system as a whole rather than focus on one single function, right? We now had the means and the methods to look at biology as a system, which also meant that we now had ways of manipulating and engineering biology and scale it up, right? So systems biology, of course, then gave birth to what we now call synthetic biology. So if we can manipulate systems, if we can manipulate biology at the systemic level, then we could also produce it. This was super exciting. This was a major inflection point in the history of biology. We no longer were limited to small functions like niche functions. We could manipulate things at the systemic level. Now, our ability to engineer biology itself is a huge moment in history. It basically means that you can produce whatever complex molecule you wanted, pretty much theoretically, right? So, which meant that there's going to be a huge change in the way we treat diseases, huge change in the way we develop new therapeutics, and even new sources of food. I'm sure all of you have heard of impossible food. So, for example, not to digress too much, Impossible Foods is a startup based in the United States trying to come up with an alternative plant source beef. So basically, they make beef, which is actually not from animals, but from plants. You actually produce that in the lab. But then all this is great, right? But we did realize that we could have gone faster. And we do realize that that speed hadn't happened in the last decade, because there was a small problem. Now, a lot of you who have learned, who have been around when machine learning was slightly different from today, where machine learning was largely dependent on a feature selection, you probably recognize this problem. So early machine learning sort of largely hinged on something called feature selection. Now, I'm sure a lot of you already know what's a feature, but I'm going to actually do a quick, a 5-year-old version of, 5-year-old child's version of what's a feature. So imagine you have, you have a fruit, an apple, and you want to teach a machine how to detect an apple, right? How would you do it? Now, one thing I could tell, I could use as a feature for this is, hey, let's look at the shape, look at the color, and look at the smell. Based on these three things, you can tell whether it's an apple or not. Okay. Now, these three things, shape, color, and smell, are called features, and they help in determining whether something is an apple or not. Now, obviously, this is not an exhaustive list. This is just an example. Now, one of the problems with this approach is that you need to know very clearly what defines an apple. Now, this is a problem when it comes to more complex things like biology. It is not always possible to list out the features in biology, right? Because we ourselves don't really understand it much, right? In biology, if you had to come up with a list of features for something, A, you need to be super specialized in doing that, right? B, feature selection in biology was so complex that it became a largely trial and error, approach, because we didn't know what works and what didn't work. And the third point is that the search space for features in biology is massive. For example, if you take your favorite molecular pathway, how do you define it? How do you tell? Let's take your favorite signaling molecule. How can you teach a machine how to detect whether something is involved in signaling? Where do you even start? How do you know what are the inputs, what are the outputs, because the network is so dense that it's like, tearing, opening up a, ball of hair, right? It's like so messy. So, and that was the problem, that massive search space for features in biology. It's easy for us to define an apple, but when it comes to biology, it became a problem. Now, that is where deep learning actually made a difference. So now, just to be clear, deep learning, although the phrase is new, the idea is not new, right? Of course, I'm not going to go into the technicalities of it, but it started off as neural networks. But some, Professor Hinton at Toronto had who is actually a pioneer of neural networks, figured out, I think, late 90s or the early 2000s or mid 2000s, somewhere around that time, that layering more neurons in the network gave rise to very interesting results. So what you have on the screen are actually like 5 different kinds of architectures for deep learning algorithms, but there must be like 25 or 30 different types of deep learning algorithms. I mean, of course, you guys probably already know that. But what this really meant, that all these layering of neurons basically meant it was a black box. You give it some input, you give it your input data, it gives you a classification at the end. No one knows what happened in the neurons in between, practically a black box. So this is our major like nuclear weapon that we have suddenly realized that we have in the last decade or so. But why is this important? Oh, it's super important because of the complexities of biology. What is deep learning super good for? We very quickly realized is, I guess you guys probably remember this as well. The internet was flooded with cat pictures of how computers can detect cat pictures, and deep learning was very good in telling you that whether a particular picture had a cat in it or not. Right now, the trick is that it could tell you whether a picture had a cat in it or not without you defining what a cat looks like. Going back to the apple, you don't, unlike the apple example, you don't have to pick the features that make a cat. You just have to give it a lot of data with cats in them and tell it that there is a cat in this picture, right? So that is called training. But the most important thing is you no longer have to define the rules, right? The promise is that the algorithm will learn it from the data. If you give it labeled data and tell it, that, for example, the cat pictures, 1,000 cat pictures, it'll know what a cat looks like, right? This particular phenomena is super useful when you yourself don't know the rules, right? Which is exactly the case in most of biology, right? There are so many problems in biology where we don't know what the rules are because the system is so complex. So like I was saying, this is sort of like a blessing this is like a massive blessing for biology in some sense, because feature selection is no longer a bottleneck. You're no longer worrying about have I chosen the right features for my classification problem. You don't. You just have to use your human intuition to label the data, and that's it. Somehow, magically, the machine learns it. Now, this is a game changer for a lot of applications. You no longer have to define the rules, like I was saying. It kind of unlocks so many applications that were previously too complex to attempt. Now, for now, I mean, we can remove the cat pictures. Obviously, the cat pictures were not really high value exercises. But what if you replace the cat picture with a biopsy, like the one on the right? Can the machine still do its trick, do its magic? And the answer was Yes, it can. Tumor classification is one of the most successful applications for deep learning, simply for the same reasons as it was very good as detecting a cat. Of course, I don't want, let's not get carried away too much. It's got massive limitations as well. And I think it's worth talking about it quickly as well. So one of the things I mentioned earlier is the black box nature of the whole system, right? Which basically leads to very poor explainability. So what it really means is it cannot tell you how it came to know or what are the features that make a cat, right? It cannot tell you how it arrived at the answer. And that is important. We not only need the right answers, but we also need the logic for getting to the right, of how we got to the right answer, right? Now, deep learning is extremely bad at this. As long as you're happy with the black box, it works great. But if you need to understand how the decisions were made, this is not the right. This has got limitations. And the need for training data, right? Now, this is in cat pictures. Hey, great. We'll find you 1 million cat pictures, no problem. But this doesn't fly with some aspects of biology, right? There are very limited data sets available, especially when it comes to healthcare, especially when it comes to fundamental biology. The expense around generating data is very, very high. So which means that there is very limited amount of data. Now, this is a problem. Now, the third point is, as we already know, biology is noisy, which means that the data is fat-tailed. For folks who don't know the phrase fat-tailed, it simply means that in the extremities of the data distribution, there is a lot of variation, right? So if you imagine this as a distribution, then fat-tailed simply refers to the fact that there's a lot of variation in the extremities. In simple terms, it simply means that there are too many, there's too much variability in the data, right? Now, this is a problem again. The more variability you have in the data, theoretically, you need a larger training set. Again, it's a problem in biology. Now, of course, this also goes hand in hand with the ever-increasing need for compute power. But compute power is something we have learned to deal with simply by throwing more money at it. We just end up spending more and more money on server farms and AWS and Google Cloud and whatnot. Job done, no problem. Nobody's worrying too much about it. There are many more limitations, but I'm going to sort of crack on now. So this silver bullet is actually making a huge impact, right? There's a lot of work being done in drug discovery and repurposing. Now, so when COVID-19 hit, you guys may remember that one of the first things that we heard in the media is drug companies looking at repurposing existing molecules for fighting COVID-19, right? Hydroxychloroquine was actually one such effort. Now, obviously, this is it was done because it's faster to get a molecule to through clinical trials if it's already existing and it's just a repurpose. And repurposing typically involves going through a lot of high dimensional data, right? And AI was used extensively for screening through thousands and thousands of molecules for repurposing. Fundamental biology also is seeing a lot of impact. Right? Gene expression studies are now largely the cutting edge in gene expression studies are now AI driven. Protein-protein interaction data, super important for a lot of different applications. Again, network biology and AI deep learning methods are coming together. Healthcare. Now, probably healthcare and drug discovery are they are two areas with the most impact when it comes to AI. Now in healthcare, a lot of the data is basically imaging data, like from CT scans, from overall from radiology, you name it. Then text analysis. So a lot of the health data is actually in EHRs, that is electronic health records. Now these are in the form of text. Now how do you extract insights from those text? That text is simply data, it's not insight. So how do you get to actionable decisions from this text? That was one of the biggest challenges, and deep learning proved itself to be pretty good at this. There are maybe, I don't know, 30 other areas in life sciences, in biology, where AI has made an impact. But I just picked these three because I think that these are the areas with the maximum impact. I actually, on the healthcare point, I want to actually walk you through a case study or or an example, and just give me a second. So this company, HEALIUM.AI, that you see on the screen, is a company that I worked very closely with. The founders, Biju Jacob and Neeraj Tiwari, came together around 6 months ago and founded this company. So it's a very young company. What Helium does is digital diagnostics for detecting chronic kidney condition. So a quick background here is that, as you may know, chronic kidney disease is actually super prevalent in the Indian population. Now, the reason is that a lot of lifestyle diseases and other comorbidities have an effect on your kidney, right? And for example, diabetes exerts pressure on your kidneys. If you have cardiovascular conditions, it puts pressure on your kidneys. All the medication that you take for diabetes, for cardiovascular conditions, or any condition is exerting pressure on your kidneys, leading to deterioration, right? That deterioration is largely undetected because it's a slow deterioration, but sometimes it can be a very rapid deterioration depending on your comorbidity. Now, right now, the current state of the art is you're going to go to the go get some tests done, like creatinine, etc. And then the specialist nephrologist tells you that whether you have CKD or not. By the time these lab results show up, it's already too late. So if a lab result has to give you a positive, then the kidney would have started deteriorating a lot already. Biju, having worked in nephrology for most of his life, knew that this could be avoided. We can potentially save thousands of people from going into dialysis, right? So that was the motivation. Neeraj, who's a PhD in machine learning, originally wanted to actually build self-driving cars, but when he heard the problem statement from Biju, he knew that this was going to be way more life-changing and impactful than self-driving cars. So what these guys put together is a complex stack of technologies such as NLP, image processing, a lot of temporal analysis, all put together, along with some really clever computational fluid dynamics. I'll speak about it quickly in the next few slides. So this is what their stack looks like, right? On the left, you have all the myriad different kinds of data types that they use, like blood tests, urine test reports, X-rays, CT scans, whatever you can put your hands on. These guys have figured out a way to use it, right? The middle layer is an integration system. It is nothing high tech. Is basically a pipeline for sucking data from all the different hospital information systems and the lab information system. That's it. And then organize that in a central database after anonymizing it. And then the other part of the stack, the last part of the stack, is their deep learning engine. Now this, what they call Helium Analyzer. Now this is the core of everything they do. This is where all of that stuff comes together, and they're able to do three things very well. They're able to screen the patients. That is based on all the data that you see on the left, they're able to tell whether, classify whether a patient has CKD or not. They're able to then detect how quickly is the condition changing. Now, this is unprecedented, right? Most nephrologists cannot tell you how quickly your condition is changing. And that is a very key piece of information for making therapeutic decisions, whether you need, how quickly are you likely to end up in dialysis, for example. So basically what their algorithm is doing is, on the left, you see all these different kinds of data sets under the heading lab tests, right? So you can see a whole bunch of tests which are typically already done on patients. Now, the beauty of their algorithm is that you don't need a complete data set for their algorithm to work, right? So there must be like 50 or 60 different lab tests one is subjected to, but they don't need all those results. They just need a few. They are able to handle missing data very, very well. And then all of that goes into their engine, and then which basically gives a classification of whether it's a CKD yes or a CKD no, and how it's changing over time. The third part of what they do very, very well, which I wanted to highlight, is this. Now, that progression that I was talking about, how quickly is the condition deteriorating or improving, for that matter. Now, I've seen a lot of companies use deep learning out of the box for some application or the other. But these guys went one step further. They did something very, very clever. They used principles of computational fluid dynamics to model and combine that with deep learning and modeled the flow of blood through the kidneys. Based on their standard model and by comparing patient data, they could model the flow of blood through the patient's kidney and then give a score on how quickly the progression is happening. Now, this is utterly unprecedented. Most nephrologists do not have access to this kind of technology, right? So these guys very quickly became the de facto clinical decision support system for most nephrologists. Like I was saying, the way they use technology to solve this problem was so insightful and clever that although they just started out 6-7 months ago, they're now in 10 major hospitals, and perhaps over 50,000 patients have already been through their system. They can truly claim that they have saved thousands of lives. And that is reflected in their revenue. They're already revenue positive. Not a lot of startups can actually claim that. And like I said, they're the default decision support system for most of the nephrologists. So this is a company which used AI and combined it with other techniques to make a difference. And not just helium. This is not a rarity. There is absolutely no shortage of people trying to take on really fundamental challenges using some aspect of deep learning. Some of the names that come to my mind are companies like Distributed Bio. So Distributed Bio is an American company which is looking at antigen-antibody interactions and how can we simulate or screen antigen antibodies using large data sets. Atomwise similarly is doing that for chemistry. Inference, for example, is using deep learning for classifying patients for clinical trials. Ginkgo Bioworks is probably the oldest company in this list. Ginkgo, you should absolutely look them up. So Ginkgo is using really cutting-edge technology to produce synthetic organisms and produce specialized molecules. So their whole business model is, if you are in the market looking for a specialized protein molecule, we will produce it for you by artificially engineering the pathways required to produce it. And they are using deep learning in many interesting ways.
Similarly, Recursion Pharma, you may have heard of them. They're a fairly large pharma company, and they're purely an AI-driven company. Right? I think most of their business is around repurposing. Of course, this is a selection of what 5-6 companies from perhaps some 300 to 400 companies across the world, which are using deep learning for some application in biology. And that is reflected in the amount of capital that is being poured into this, right? So I also want to give you an idea of what is happening on the other side of the fence. Yes, the technology is fine to talk about the technology. Let's talk about what it's doing in the real world. So AI in biology companies have been raising unprecedented amount of capital. So if you look at the graph, basically it's the amount of funding raised by these companies over the years. And an interesting thing in this graph is it all starts changing around 2012, 2013, right? So 2013, if you think back, is the time when deep learning really came to being. I think by 2009, 2010, the first ideas had already been published by Hinton Lab. But by 2013, it started becoming mainstream. People started talking about deep learning. And that is when you can see the graph changing its trajectory and to really unprecedented levels now in 2019. And these investments are simply not, experiments. If you look at how these investments are being made, it's actually, if you look at this chart now, I hope everyone can read the chart. Some of the fonts are actually kind of grayed out, but what it really, the colors indicate the stage of maturity of a company. Series A is the youngest, Series B is older, Series C is much later, Series D, E, F, and so on, right? So now you can see that although the companies in 2014, most of the investments were made in super young companies, mostly seed and Series A. You see black and green here in 2014. That starts expanding from 2015 onwards. And by 2018, you see a lot of Series D companies here that are being funded, and some Series E as well. 2019 is totally different scene. So much money is being poured into much later stages of AI biology companies. What does this tell you? This basically is evidence that the technology is maturing, really making a difference, right? And the world is acknowledging it. Market is acknowledging it. And it's not just money flowing in, there's money flowing out too. These companies are getting larger and larger, and their exit values are also reflected in it. 2018 saw some really high value exits in this space. On the other hand, investors have also kind of started to realize that the returns are pretty healthy on in biology. So this is not just this graph is not limited to just AI in biology. I couldn't find the split for AI in biology, but this is for entire biotechnology, and this is kind of reflective as well. So if you look at this graph, you have value or investment multiple on one axis, and the year on the other axis. The green values plotted are basically the multiples. So a multiple is nothing but how much money you make out of your investment. So if I invest 100 rupees and I get 200 rupees back, then I made 2 times the money I put in, right? Very simple. Now, this compared to tech investing, that is, when investors talk about technology, they are mostly referring to software industry, right? Most investors are not referring to biotech, and it's always been sort of distant because it was always considered hard to do. Actually, you know what? It is not true. These numbers indicate that the returns in biology are far than in even in the software industry. So the basic takeaway for you is that AI technologies are not just enablers, but have also sort of unlocked sort of a gateway in biology. All the downstream effects are going to be multiplicative. That is, you're going to see a lot and lot more of this happening, and biology taking a completely different approach in the coming decades. Of course, when it comes to deep learning, it is very clear we're still in very, very early days. Some of the problems that we have with deep learning today are indicative of it. Even when we try and use the phrase artificial intelligence, we are so uncomfortable with it, right? Because the entire idea of artificial intelligence is generalized intelligence. That is a machine trying to reason its way through regardless of what's thrown at it. Of course, we are very, very far away from it, right? This actually seems like a toy in front of what generalized intelligence is supposed to be. This is nowhere close to it. But pretty much everyone has to acknowledge that this is a start, right? This is going to play out for many, many decades to come, and it is a start. And of course, for a complex area like biology, it is right now, it looks like we have the tools to deal with the complexity, and just acquiring the tools to deal with the complexity. So it's a great time to be in biology, and of course, it's always been a great time to be in computer science. So that is actually what I wanted to talk about when it comes to AI and biology. However, I'm going to spend a couple of minutes talking about what Entrepreneur First does, simply because it may be of interest to some of you who are thinking about perhaps starting companies in the future. So Entrepreneur First is basically like a venture capital company, right? But the difference is that we focus on finding sort of exceptional, talented, and ambitious people from academia and industry, and help them build impactful large startups. And we do that by offering three things. One is help them find co-founders, help them sort of mentor them through ideation, give a structure to the whole ideation process, and help them sort of put together a viable business. And also help them in their journey forwards by putting in pre-seed investment. So essentially what Entrepreneur First does is provide you with a safe space to build a deep tech company. So the safe space, what do I mean by that? So firstly, there is a stipend of $2,000 for the 6 months that you are with us. And which basically gives you the financial protection or financial security to safely think about starting a company, right? You don't have to worry about not having an income. Second is you get to meet incredible people from other top-notch places. The bar to get into EF is so high that the other, very likely that the other people you meet are at the forefront of whatever they're doing. And there's a lot of structured mentoring from experts. So basically, we have venture partners and experienced entrepreneurs mentoring the people or the teams within EF. And our fund is very specially designed for building deep tech companies. So it's not, you're not competing against, let's say, B2C or e-commerce companies or fashion companies for raising capital. We know exactly what deep tech is. So we have a completely different perspective for when we assess your risks. And of course, there is a global alumni network. So EF is present in 8 different locations across the globe. And in every single of these locations, the bar is super high to get into EF. So the alumni network is very valuable, needless to say. So if you're interested in becoming an entrepreneur anytime in the future, I would suggest that you go to joinef.com and apply. So that brings me to the end of my talk. We still have just over some 5-6 minutes. I'm super happy to take questions at this point. I'm going to stop sharing my screen so that I can actually see who I am talking to.
Yeah. So Prajwal, I'll be reading the questions from the panel, and you can answer them. So the first question we have is it's a very specific one, I must say. A lot of parameter values in biology vary from cell line to cell line. So how do we overcome this drawback?
Well, so that is a part of the problem, isn't it? So even we see cell lines as a same thing but slightly different, but biology doesn't have any such distinction. If you have a separate cell line, you have a completely different rule set or a parameter space. So your question is basically around, are there better tools for figuring this out? Right now there aren't, primarily because you do not have enough data from each of those cell lines to be able to teach the computer that these are separate cell lines. Right. I mean, that's literally the underlying problem.
Yeah, I think that I hope that answers that question. Shall we move on to the second question?
Yes, please.
So the second question is, don't you think that using machine learning based approaches is making biology less of a science because you're not learning anything about the biological process itself?
Very good question. This is actually one of the big challenges here. Like I was saying, everything is sort of moving towards a black box kind of approach. You generate large data sets and throw it into a black box, and something comes out, and you publish a paper, and you get your degree or whatever. It is indeed a problem. A lot of the experiments go unexplained, as in without us actually gaining an understanding of the underlying phenomena. It is definitely a risk. I completely acknowledge that.
But again, if somebody is like looking very deep into the algorithm they're using, maybe they can get some insights from that as well, if they want.
Possible, but I think what's happening right now is we are not at a place where people who are able to articulate what is happening, what kind of weights are being distributed within the algorithm, for example, and how actually biology works in that particular instance. I don't think we have the skill sets just yet. I would say that in the coming decade, when we'll see a lot of computational biologists being trained in this area, even mainstream biologists being more familiar with computing techniques, this is more and more likely to happen. That we'll start figuring out the underlying phenomena.
So over time, we'll have even more insights as also our understanding of the algorithm themselves also increase.
I think, yeah, you're right. I think a lot hinges on us understanding what's happening in the algorithm rather than what's happening in biology first. Let's figure out what it is that we are doing so that it helps us understand where we are applying it.
Yeah, that's pretty much summarizes the thing. Moving on to the next question. So the next question is actually how to utilize artificial intelligence, specifically when it comes to biology of stem cells.
That's a super specific question. I'm not familiar with the stem cell area, so I'll have to pass that question, I'm afraid.
Okay. No issues.
Unless you have a follow-up question on that, is there a specific phenomena that you're referring to, etc.? Maybe I could give you a generalized answer, but yeah.
I think they expect a generalized answer here, I guess.
Okay, could you repeat the question? Maybe I got it wrong.
So the question is just how to utilize AI in biology and stem cells. That's it.
I mean, at the end of the day, the questions that you want solved are kind of similar if stem cells or otherwise, right? They're mostly either on the fundamental level, for example, protein-protein interaction, figuring out signaling pathways within those cells, or something to do with the surface proteins if you're very worried about some kind of off-target interactions that you weren't expecting. So stem cells do not have any special questions for them. I mean, the same questions you would ask generally in biology, you would ask with stem cells as well. And similarly, you would apply the tools, same tools to them as well. It depends on, I guess, what kind of hypothesis you are going after. So, for example, if you're looking at why certain cell lines produce a particular kind of protein and not some other kind of protein, then you're literally asking, how can I deduce that molecular pathway? And then you are, basically fishing for data that can help you solve those questions. So I think long story short is that the same questions that are generally applicable are applicable here. It is. I'm afraid I'm not able to answer that very specifically, simply because it's a vast field. I mean, we can sit for like weeks and talk about it.
I mean, anyways, if you are able to boil it down to the same fundamentals, it's the same thing.
Yeah. Unless there is a specific phenomena within stem cells that you're referring to, I'm not sure how to answer that.
Yeah, I mean, if they can, I mean, general sense is the same thing, I guess.
Correct. Yes.
Yeah. So moving on to the next question. So this is something I have also somebody else has asked, and also I have in my mind itself that if you are looking at opportunities for us, let's say as UGs or some in the future. So like I'm just a second year UG, so there might be some other seniors of me as well. So what opportunities are there for us in this kind of a field?
So I'm assuming you are either in computer science or some kind of engineering discipline or biology.
I mean, there might be some people interested in that as well. So yeah.
So I think the time has come where you start specializing, right? I think technology in the next decade is going to be so sophisticated that it makes sense for you to sort of specialize, but not find yourself in a super niche area. Please don't do that. Basically, if you are in, let's say, computer science, try and figure out what are some of the interesting challenges, basics of biology. You can do that in a lot of the online forums and platforms. You can absolutely basically be familiar with how biology works, some of the fundamental challenges, but more importantly, just focus on your subject area, which is if you're learning machine learning, then just be an expert in machine learning. A good an engineer will extend himself to any topic. That it should be fine. There's nothing special to do here, but if you want to sort of speeden up your understanding of AI in biology, then I would say start solving problems in biology. Start looking at things like gene function prediction, protein-protein interaction. Start looking at protein folding, for example. These are hard problems in biology. Yeah, that's a good start, man.
Okay, so a certain question that ties with this, I guess, is that what actually are the opportunities of entrepreneurship in biology? So how does this actually tie into biology?
Yeah, great question. So there are two kinds of opportunities in biology today, right? So one is in the past, what happened was if you were a biologist, most of the technology was around a wet lab. So either you're coming up with a new technique or you're coming up with a new kind of end product. Now, for that required a lot of capital investment, and whoever is making the capital investment had a lot of risks because biology is noisy. It's fraught with risks, and there are a lot of trial and error. So you needed investors who had the stomach for that trial and error and that risk. So in places like India, it got a slow start because there were very few avenues where you could go get that kind of grants. Now today, that has changed. You have the government supporting student entrepreneurs quite extensively through grants like BIRACS, BIG. I'm sure a lot of you have heard of BIG, and then there are follow-on grants as well. Now the second aspect that is new now is if you want to solve problems in biology, you no longer have to be just a wet lab scientist. You can also be a computer scientist. Now, one of my favorite topics these days is antigen-antibody interactions, for example, right? Antigen-antibody interactions are so complex. The search space for what is, for these interactions is massive. Now, it is also a computational problem because you have all this data available. You can start building, you can imagine building products around this, right? You can be purely a computer scientist and still solve problems in biology, which means that there is space for companies, software companies in biology, right? The next generation of companies, actually some of them which I mentioned earlier, are purely computer, in silico, right? Distributed Bio, the company that I mentioned, is fully in silico. They do not have a lab, like a wet lab. So there are hundreds of problems in biology, which, for example, which people like the pharma companies and biotech companies are very happy to pay for, that are purely in silico, right? Which means these hurdles for starting up are very, very low. All you need is a computer and access to, I don't know, AWS or something, right? And a lot of these data sets are actually in the public. So you can actually make a start with very less.
Yeah. So basically, that the integration between all these fields in the current time has helped, whatever person there is to get a kickstart very easily.
Yeah, absolutely, absolutely. So that is also reflected in the funding figures that I showed you. The amount of money being poured into companies that are purely in silico is going through the roof, right? And in a time like today, you do not have to restrict yourself to what India is doing. It's actually, everything is actually pretty global. You can see investors across the world happy to invest in Indian companies as well. So pick the problem you are most excited by. Figure out who it is that is likely to pay for it, right? Today, pharma companies are open to paying for in silico products. It was not the case 10 years ago, right? You go to a Pfizer, you go to a Shire or Johnson & Johnson, they have their own in-house in silico R&D, right? Which means that they are also thinking about this, which means that they're open to spending money to do business with startups. This is like the massive writing on the wall. Now is the time to start companies in this space.
Before moving forward, I'd like to ask you that actually we have overshooted our time. So do we have 10 more minutes? So do we have a few more questions as well?
Yeah, happy to spare.
So for the next three questions, I'd like to combine them because they are targeting this same thing, which is the models themselves. Mm-hmm. So at the end of the day, we have a black box thing in the machine learning models and all. So we can't be 100% sure about it. So what kind of a surety level are we looking at, and so what kind of thing it takes for the practitioners and all the people who actually will be using this model? So what kind of a surety do they have when it comes to the models? So essentially, that are they using it as it is, or are they very doubtful about it?
I'm not sure I understand the question though.
As in, the machine learning models are 100% accurate, right? So
correct.
The people in the field, who actually will be using all these models, so are they let's say I have a medical practitioner, some doctor. So are they before prescribing, before using after using the model, they have some result. So after using that result, are they 100% sure about it, or are they very doubtful about it? So where do they lie this time?
Okay, great. So if you look at healthcare, wherever AI has found some traction or found some success, as in the case of helium that I was talking about, it is almost always the first line of defense, right? It's not the last line, it's always the first line. So even if I go back to the helium example, what happens there is when a patient comes into the hospital, for example, and the algorithm says, this person is likely or very susceptible to CKD and flags the patient is just taken on a different workflow now. That workflow includes a visit to a nephrology specialist and a whole bunch of lab tests, etc., as confirmatory exercises, right? So the point is, you obviously don't want these models to be perfect just yet. They just need to be better than what we're already doing, right? Because then you can deploy them as the first line of defense and then do confirmatory stuff later and confirm it, right? And back it up. So perfection is probably, this is one of the places where perfection is the enemy of good, where you just need it to be better than what we're doing.
And obviously we're able to combine all the human elements inside it as well.
Exactly. That itself brings in a lot of value.
Also, one more thing related to all the usage of data as well. So in the current times, we also have a lot of fad about privacy and all. So like patients might care about their privacy more than their disease sometimes as well. So what are the measures about that? How are we able to maintain privacy of patients?
Interesting. I can think of two things that are happening in this space. Firstly, there are places where privacy is not given an importance, sadly. And that has to change. At the same time, there are technologies that are coming up purely to protect privacy for such applications. Let's go back to healthcare. Now, in healthcare, what happens is that you have a hospital information system or a electronic health record system. Now that has its own software protection, like firewall, so on and so forth, right? Now, on top of this, there are technologies available today which will basically take that data, localize basically anonymize it locally, and then only ship the metadata to a cloud server, right? The metadata is completely anonymized. So people are using edge computing techniques to solve a lot of the privacy issues, especially when it comes to healthcare, simply because people are actually concerned about privacy. So even some of the major hospitals in India are investing in systems like this. So things are changing.
Yeah, we can also even fit the fields of cryptography and all when it comes to privacy as well.
Absolutely. Again, it's being solved in two ways. One is anonymizing at source, right? And then encrypting the data itself, right? The two separate strategies, but it's happening.
Yeah. So that I think answers the ways about privacy. So yeah, actually I got the answer from the person who was asking about stem cells. So they're asking specifically about designer babies and also 3D printed limbs.
So I know about 3D printed materials a bit more than designer babies, I would say. So I'll just take that. I absolutely have no exposure there. So I know a lot of interesting things are happening in 3D printing, especially in bio. There are so many different applications in tissue regeneration, and especially around the eye. I think cornea is a big target for regeneration. And then there's so much happening in cosmetics, for example. You have 3D printed models of the skin for testing out drugs, for testing out various kind of cosmetics. I could go on and on, but the way machine learning is working there is simply by in the iteration, because what I think we have to sort of accept now is that biology has become an iterative technique, right? A lot of techniques in biology have now become iterative. You can try something out. If it doesn't work, figure out what didn't work, and you do it again until you get it right. And the data collected during this process are completely amenable to machine learning. You can make this better and better with machine learning.
Yeah. I don't have anything to add from my side. So the last question I think we'll take is about the very current times we are facing, coronavirus and COVID. So how has ML been used in COVID research?
From what I know, one is drug repurposing. So almost all of the large pharma companies looked at their portfolio of small molecules and put together large screening exercises for repurposing for coronavirus. So you may remember that in, I think, March, April, there are a lot of reports on various different candidates that were being discussed in the media as possible interventions for for COVID-19. And pretty much all of them had some element of deep learning in them. This is also sort of supported by, if you do a Google Scholar search, or for around this for drug repurposing, you'll see that a lot of new stuff has been published around COVID-19 and AI in it in the last few months. The other way is, I've heard that for companies that are going after vaccines, organizing clinical trials was not easy. One of the challenges there, as you know, is coronavirus is so dependent on comorbidities, right? You have extreme outcomes depending on what the comorbidities were. So some people just walked away from it, like with a slight fever. Some people sadly lost their lives as well. So this variation is because of comorbidities, and which means that in a clinical trial, designing the cohort for clinical trials is a massive challenge, right? You don't know what to exclude, you don't know what to include. It's absolutely a huge challenge. I hear that this was done using various different machine learning models by a lot of these companies, especially AstraZeneca.
Yeah, the one developing the Oxford vaccine. Yeah, so I think the machine learning has actually quite a bit sped up the process. I feel that what would have been not possible if we have not been using models, and also the process for let's say vaccine development and drug development has been sped up quite a bit, thanks to all the models we have earlier as well, and newer models that have come in. Yeah, so that was the last question. So I think I'd like to thank our guest speaker today, Dr. Prajwal Bhat, for giving such an informative talk, such a meaningful talk to all the attendees and all. So, and also taking the time out of a busy schedule and listening to coming on our request to deliver a talk in the Pravega Paradigm series. So thank you for that.